Okay, ladies and gentlemen, the first thing we're going to learn about today is Hess's law. So let's get right into it and find out what Hess's law is. Okay, so first off, before we explain what Hess's law is, let's explain something real quick. Because Hess's law is what we call state function. What is a state function, and why do we care? A state function is a certain type of quantity. As you can see in the first bullet point here, it says a state function is a quantity that is independent of path. It only depends on the initial and final states of the process. In other words, it doesn't care how it got from point A to point B. It doesn't matter how we got from 5 degrees Celsius to 20 degrees Celsius. As long as we got there, that's what matters. Okay, so a state function is independent of path. A non-state function, there's a second bullet point here. A non-state function differs depending on the path taken. So how you got from A to B really depends. So how far you traveled, or how far you walked to get from here to the store really depends on what path you took. Straight up the street, or did you go around and then come back around? If you went around and came back around, you probably went further than if you went straight up the street to the store. So those are path independent states. So examples in thermochemistry of non-state functions are Q and W. Q, remember, is heat, and W is work. How you did something will give you a different Q. And how you did something will give you a different W, different work. But state functions, these delta quantities, are all examples of state functions. And so delta E is a state function. Change in energy is a state function. Delta H, the change in enthalpy, is a state function. And delta T is also a state function. As I said earlier, how you got from 5 degrees to 25 degrees doesn't matter. As long as you got from 5 degrees to 25 degrees, your answer is going to be the same. Okay, so those are examples of state functions. Turns out delta H is one of these state functions, and we're going to take advantage of that. And that's where Hess's law comes in. Hess's law comes in because since delta H is a state function, it doesn't matter if a reaction is completed one step or many steps. The enthalpy change is going to remain the same. As long as you go from one set of reactants to one set of products, it doesn't matter if you did it right in one shot or if you did it step by step by step. Maybe you did it in a series of 3, 4, 5 reactions. It'll be the same. Okay, the delta H will end up being the same. So you can calculate the delta H of a chemical reaction if you can find other reactions that, when added together, give you the chemical reaction in question. They may be different reactions. They may not even be parts of the reaction, the way that your reaction takes place. But if these other reactions add up to the reaction that you're looking for, you can take their delta H's, and then you can use those to calculate the delta H of your reaction, and we'll see that in a little bit. So here's an example. Let's say you wanted to figure out what the delta H is. When sulfur reacts with fluorine to form sulfur tetrafluoride, SF4. Maybe you know what the delta H is for the reaction when sulfur reacts with with fluorine to form sulfur difluoride. And then maybe you know what the delta H is for when that sulfur difluoride adds another F2 to make sulfur tetrafluoride. So if you know those two delta H's right there, if you notice, by adding these two equations up, you get this equation. And if we go ahead and add them up, there's going to be SF2 on the right-hand side here, SF2 on the left-hand side here. Those are going to cancel out. There's going to be two F2s, just like we have over here. So you're going to end up with this equation by adding these two equations up. Well, if you get this equation by adding these two equations up, that means that the delta H of this equation is the same by adding these two up. Now, that was kind of a simple equation, example, and I just wanted to show you that because you could see kind of pretty easily how that could work. But we got other examples that'll show you kind of the same thing. So this is Hess's law, right? Take two equations, combine them together, and then the equation that gets combined, once you've added those two equations together, you just add up their delta H. And here you notice this is a negative 292 kilojoules. This is a positive 43. So you just add those two together, you're going to end up with something like negative 249 kilojoules to be your answer right here. So the delta H of this one should be negative 249 because that's what negative 292 and 43 add up to be. This delta H is these two added together because this equation is these two added together. Now, you're not always going to get them exactly like that. Sometimes you're going to have to manipulate the equations in order to get them to line up and add up like you'd like. So sometimes the chemical equations can be manipulated to help attain the equation in question. In other words, the equation that you're looking for. How do you get it? Well, sometimes you have to manipulate the other equations. Here's a couple of manipulations you can do. Number one, if you reverse the direction of a chemical equation, once you've reversed the direction, in other words, you take the reactants, turn them into products, the products, you put them on the side of the reactants, right? You've got the reverse reaction. What you do for the delta H is you multiply it by negative 1. Positive 500 turns into negative 500. Another thing you can do is if you multiply a chemical equation through by any number, you just multiply the delta H by that number. You need to take an equation and double it, double the delta H. Take an equation, multiply it by 5, so multiply every coefficient in that equation by 5. Then what you're going to do is multiply the delta H by 5. Okay, so those are two things that we can do in order to get our equations to line up so they add up to the equation that we'd like to find the delta H for. So here's some examples. Here we've got N2 and H2 reacting. They form 2NH3. Delta H of this reaction is negative 92.4 kilojoules. Now, if I want to switch it so that the NH3 ends up on the left side of the equation, right? Here on the right side, now it ends up on the left. And my N2 and my H2, my reactants, end up on the product side. So basically, this reaction here, the second one, is just the reverse of this one. So if this one was negative 92.4, because I reversed this one, I'm going to take the negative of negative 92.4, and that's going to give me positive 92.4. In other words, just switch the sign, reverse the sign. That's one of the things you can do, or one of the manipulations that we can use. Another example here is we have this equation right here. What we did here was we went ahead and we took this initial equation and doubled everything, multiplied it by 2. So if you multiply 2 to this whole equation, 2 times 1 is going to give you 2 here for the N2. 2 times 3 is going to give you 6 for the H2. And 2 times 2 is going to give you 4 for the NH3. So you've doubled the whole equation. All the coefficients are doubled. What happens to delta H? It gets doubled too. Negative 92.4 multiplied by 2, it's going to give you a negative 184.8 joules. Units here, you know what I mean. Okay, so if you multiply this first equation by any number, you multiply the delta H. And that gives you the delta H for this reaction. Even if you multiply it by a fraction, let's say you want to half these things. So you multiply this equation by 1/2. All right, so you end up with 1/2 N2, 3/2 H2, and 2/2 or 1 NH3, and that's what we have over here. So since we multiplied this by 1/2, we also multiplied the delta H by 1/2. That's still that second manipulation you can do. It's just I'm using fractions here instead of whole numbers. So 1/2 of negative 92.4 is negative 46.2 kilojoules. How that works? Now, this is not the full equation. You might be asking, well, when will I use that? How will I know if I want to use that? Why would I want to multiply an equation by a certain number? I'll show you an example right here. Okay, for the sample problem that we have here, Sulfur and oxygen form SO2, sulfur dioxide. We want to know what the delta H is. We don't have it. We do have the delta H for a couple other reactions. So let me go ahead and get my pointer out. Okay, so over here, we do know that for sulfur, when it reacts with 3/2 O2, it forms SO3. And the delta H for this reaction is negative 395.2 kilojoules, as is shown right here in this first equation. Two different equations. We know the delta H for this one, but not for that one. We also are given the information that when two SO2s react with an O2, they form two SO3s. The delta H for that one is negative 198.2 kilojoules. So the trick here is to try to get these two to add up to form this equation. Now, right now, it might look like you can't add them up. They don't give you the equation we want, but we're going to manipulate them so we can get that. Because if we just added these up, right, so you add all the reactants together and all the products together, you're going to end up with just 3 SO3s on the right side. There's an SO3 here and 2 SO3s on the right side. That doesn't leave you with an SO2. Okay. And we've got a whole bunch of oxygen on the left. We only need one O2. The 3/2 O2 here, if we add it to this O2, that'd be another 2 halves. That's a total of 5 halves O2. Right? So what we're going to do is we're going to manipulate things a little bit. One thing you're going to notice is that our final equation has SO2 on the right-hand side. The only SO2 in these two equations over here is over here on the left-hand side, the reactants. And there are 2 SO2s. So we got to do a couple things. Number one, we got to flip this so the SO2 ends up on the right-hand side. And we got to have it end up with only a 1 as a coefficient. So what I'm going to do is I'm going to go ahead and flip it. And, first thing I'm going to do is I'm going to half both of these so that I only have one SO2. So I multiplied the delta H by 1/2. This one. There was 2 SO2 and an O2 from 2 SO3. Delta H was negative 198.2 kilojoules. I multiply the whole thing by 1/2, and I end up with SO2 plus 1/2 O2. It's okay to have fractions at this point, not in the overall, but sometimes you're going to need fractions while you're doing the problem. Form an SO3. And what we did is we halved the delta H. In the previous, before, it was negative 198.2 before we halved the equation. But now that we have the equation, we also have the delta H. But we don't want the SO2 on the left side. We want it on the right side. So not only are we going to have to half this equation, but we're going to also flip it. And when we flip it like that, so now we end up with SO3 on the left and SO2 plus 1/2 O2 on the right, which is the opposite of what we had before, right? Before, SO2 and 1/2 O2 were on the left of the arrow. SO3 was on the right. But by flipping this, now we've changed the sign of the delta H. So now this becomes positive 99.1 kilojoules as opposed to the negative 99.1 kilojoules we had before. Why did I do that? Once again, to get my SO2 on the right side, because my ultimate equation wants SO2 on the right. By doing that, I moved my SO3 over here to the left too. So now there's an SO3 on one side, SO3 on the other. They're probably going to cancel out later on. Now that I have my SO2 in position, my sulfur is already in position. I add up the two equations. And when you add up any two equations, what you're going to do is going to take all the reactants and put them on the left side of the equation, and all the products and put them on the right side of the equation. So if I were to go ahead and do that, there's a sulfur, 3.5 ox O2s, and an SO3. So sulfur, and I'll get to the O2 in just a little bit, and an SO3. On the right side, if I add these up, there's an SO3, an SO2, and 1/2 O2. So I'm going to go ahead and put the SO3 and the SO2 down. What happened to the 1/2 O2? Well, just to save time and space, I canceled this half O2 with one of the half O2s over here. That's why we ended up with only one O2 on the left-hand side. So subtract a half O2 on this side, subtract a half O2 on this side. 3 halves minus 1 half gives you 1, 2 halves, 1 O2. So we still have an O2 on this side, but there's no O2 here. Got rid of it. So now this is my resultant equation. This is what I get when I add these two equations. Now, I told you I want this equation. This one is not exactly this one yet, but you'll notice that this equation has SO3 on the left, SO3 on the right, and since they both are the same thing, just like you did math, you can go ahead and cancel the two out. And by canceling the two out, now you're left with, once we get rid of the SO3 here and the SO3 here, you're just left with an S and an O2, going to form SO2, which is the equation we want. Okay, I'll be doing more sample problems like this because they take a little practice, but I'll be doing more of them on a separate video just to show you how that works. Now that we have the equation that we want, now we want to figure out what the delta H is. And remember, in order to get this equation, all we do is add these two. Now, these two were manipulated. So these aren't, at least this one isn't the delta H we started off with the original problem. But this is the delta H that we have now. Now, if I add these two equations, I get this one. That must mean that adding these two delta H's gives me the delta H that I need. Negative 395.2 kilojoules plus 99.1 kilojoules is going to give us, that's what I did, I added two up, negative 296.1 kilojoules. That is your answer here. As I mentioned, I'm going to be doing a couple more example problems having to do with Hess's law, so you can kind of see how you can decide how you would like to manipulate the equations, maybe you would like to reverse some or multiply them by a number, and how you would know. Really simply, I just looked at the final answer here. I need the SO2 on the right, and that's not, I wouldn't start off with the SO2 on the right. I had to flip this equation to get it on the right, start off on the left. And you know, you will see later on from some of the sample problems when you'll decide to multiply it by 2. This one, or multiply by a number. This one, I decided to multiply by 1/2 because I needed the SO3 to cancel out with the SO3 here. And I also need only one SO2. The original problem had two SO2s on the left-hand side. So I needed only one SO2. Okay, that's how you do a Hess's law problem. All right, what is the heat of formation? Heat of formation is represented by the delta H subscript F. I'm going to go ahead and get my laser pointer here. Heat of formation is represented by this symbol here, delta H subscript F. We've seen other delta H's with other subscripts, heat of vaporization, heat of fusion. This one, delta H with the subscript F, is heat of formation. What is it? It's the energy change associated with the formation of a substance from its elements per mole of that substance. And the substances we're talking about generally are compounds. Okay, let's go ahead and take a look at what we mean by that. So the heat of formation of carbon dioxide, if you look it up, because these things come from a table. We have tables of these. The heat of formation of carbon dioxide is negative 393.5 kilojoules. What that implies is that in order to make carbon dioxide from its elements, as you can see, carbon dioxide is made up of two elements, carbon and oxygen. And oxygen being a diatomic element, we're going to be looking for it to come from O2. So the chemical reaction here, carbon plus O2 goes to form CO2, is the equation that describes the formation of carbon dioxide from its elements. Here is being made from carbon and oxygen. Delta H associated with that reaction is negative 393.5 kilojoules. The chemicals give off 393.5 kilojoules in order to make carbon dioxide. That's what a heat of formation is. It's how much energy it takes, what's the enthalpy change involved with making a compound from its elements. The heat of formation of any element, carbon, oxygen, hydrogen, all by themselves, sodium, is 0 because it takes no energy to create an element from itself. But to make a compound, we have to kind of put them together. So there are delta H's involved with that. So this here is a table which you will not find in page 316, and it will be called table 11.6, and that's because this is from an old book that I used. But this table is a table of heats of formation. So all of this right here are substances in this column, and this is a table. There's a column for substance and its heat of formation, all in kilojoules per mole. So aluminum oxide, yes, heat of formation is negative 1676. For CH4, methane, heat of formation is negative 74.86. Those are all in kilojoules per mole. Okay, and so basically what that means, in order to make CH4 from carbon and hydrogen, you have to, you're going to get out 74.86 kilojoules for every mole of methane that's made. Same thing with this one. For every mole of aluminum oxide that's formed from aluminum and oxygen, um, we, uh, we get 1,676 kilojoules out of the chemicals on that. Sometimes, most of the time they're negative. Sometimes they are positive. NO2 down here, so you can see, is positive 33.85. In other words, in order to make NO2 from nitrogen and oxygen, you have to take the chemicals have to suck in kilojoules per mole. So, how are these going to help us? Last lesson is on how do we calculate delta H's for chemical reactions, not just specifically chemical reactions for how you make the substance from its elements, but any chemical reaction. Well, we're going to use these heats of formation, and we're going to be using an equation that looks like this. Remember that delta H is a state function, as we said earlier in the video. So that means that the delta H for reaction can be calculated by using the heats of formation for the reactants and the products. I'm not going to go into all the details and how we can basically use the heats of formation to represent basically a whole bunch of equations coming up to the equation that we're looking for. Question. It's going to give you the equation. So the delta H for any chemical equation is equal to, see this kind of squiggly E looking thing? That's not an E, that's actually a capital Greek S. It's called sigma. And some of you may have seen it if you ever watched movies on with fraternities and stuff. They like to use Greek letters, and sigma seems to be a popular one. But in math and science, we use sigma to represent summation, or sum. It means add up all this stuff. You know, if I do sigma of all your test scores, that means add up all your test scores. So what we're going to do here is use the sigma to represent the summation of all the products or reactants. And so here's the equation. The delta H is equal to the sum of, and that's what how you say it when you have sigma, the sum of the heats of formation of the products. Each one, see this N, that represents the coefficient of each product. So you look up the heat of formation of every product, and for each one of those, you multiply by the coefficient that's in the equation, minus the sum of the heat of formation of the reactants, each one multiplied by its stoichiometric coefficient. So basically what you're going to be doing, and I'll show it down here in another way, is you're going to be looking up the heat of formation of every substance in a chemical reaction. Here's a hypothetical chemical reaction. Let's say we have substance A reacting with substance B, going to form substance C plus D. Let's say that the coefficient for A is M, the coefficient for B is N, the coefficient for C is P, and the coefficient for D is Q. What I'm going to do is I'm going to look up the heat of formation for each of these. And my delta H for this reaction is going to equal to, remember we're going to start off with the products and subtract the reactants. The heat of formation of C times P, because P is its coefficient, plus the heat of formation of D times Q. Those are my two products. And each one I multiply by its particular coefficient. And then I subtract the sum of the heat of formation of substance A multiplied by the coefficient M, plus the heat of formation of substance B multiplied by coefficient N. So I add these two together, and whatever the sum is here, I subtract that from the sum of the heat of formation of your products over here. That's going to give you your delta H for the reaction. Okay, so I'm going to do a couple of sample problems on the sample problem video that show how to do this problem. But basically, you just kind of look up the heats of formation for each substance involved in a chemical equation. Look up them up for the products, multiply by their coefficient, add them up. Look them up for the reactants, multiply each one by its coefficient, add them up. Then you subtract this from this number minus that number, and that's your delta H. Um, you'll see it's pretty simple. I think it's easier than Hess's law, but we'll see that in the sample problem videos.